So thank you very much, Alikram, for the invitation. Thank you for being here. I also share the sadness for the catastrophic event that happened in Turkey recently. Probably some of you have people you know and or relatives that suffered or died. So tragic moment. Okay, so this lecture, so I will give on the whiteboard. I will give it, and it's about a journey. Let's say my field of research is the foundations of quantum mechanics. So it will be a journey that I hope I will be able to convey you from that starts with the fundamental questions about the meaning of the theory, the meaning of quantum theory. So this is an institute about fundamental sciences, fundamental research, so it's important to talk about that. And we'll end up with very practical technological applications, in particular quantum cryptography. And it's nice to see, once again, it's not the first time in history, in the history of science certainly, but it's nice to see once again that people working in apparently not practical questions, philosophical questions perhaps, and for many people also at those times considered useless questions, eventually brought to a new understanding of physics, a new understanding of nature, and also to practical things. Again, cryptography, quantum cryptography is one of them. And in passing by, I will try to give you, probably most of you already know, but I want to highlight some points about the Nobel Prize in Physics that was given last year to Aspect, Clauser, and Seilinger. So why did they win the Nobel Prize in Physics? Incidentally, the motivation given by the Nobel Prize Committee is partly wrong. It's not the motivation of the given Nobel Prize is correct, but the motivation is that we come to that is not entirely. So we'll take the occasion to highlight a few things. And basically, the story starts 100 years ago. So we are in the 20s, so now it's 2023, so in 2 years there will be one of the anniversaries of quantum mechanics. So quantum will depend the way you want to count years. When Planck discovered the black body radiation, or when Schrödinger and Heisenberg found the final equation. So 1900s, so 123 years ago was in a sense the official start of quantum mechanics, but 100 years ago, in 2025, will be the anniversary of modern quantum mechanics, which is when it has been formalized in the way we use it. And so, we'll go in a gentle way. So we have the axioms of quantum mechanics. So the state, and that's the origin of all the problems, the state in quantum mechanics are not points in physical space, like in classical mechanics, which move with some velocity and follow trajectories. It's not like in electromagnetism, a field in space-time. It would be like, instead of being water, or being air, it's an electromagnetic field, but it's a field in space-time. Now we have a different kind of field, which is a wave function. And that's belonging to the Hilbert space, which is not physical space, and that's the source of all problems, as we will see now. So what is the meaning of a state being described by a wave function in an abstract space? But okay, we take it for the moment. So the states are given by wave function in a suitable Hilbert space, depending on the system. The dynamics is given by the Schrödinger equation. The Schrödinger equation has nothing to worry about. So first of all, it's a characteristic feature. It's a linear equation, so you have the superposition principle that we will know probably of. But otherwise, it's not a problematic equation. It's a dynamical equation like any other. It's a deterministic equation. Okay, so in the quantum indeterminism doesn't come from the dynamics. It's a deterministic equation. Once you know the initial state of the wave function, it is the principle, of course. On the practical level, there are uncertainties. But in principle, if you know the initial state, you know everything about the future evolution of the wave function. And then, that's the problematics, they come measurements. So then there are all the axioms about the measurements. The measurement, you have to choose an observable. The observable is controlled quantum mechanically by an appropriate self-adjoint operator. And that is something already that if you really think, and now then people get used to that, but if you really think, so why? An observable, which is something that you see, should be related to this highly abstract mathematical object as a self-adjoint operator, whose eigenvalues are the physical quantities that you see, and the eigenvectors are the state where the system ends up after a measurement. Why is that? You can take it as that's life, but you can ask also why is it. Actually, I will not have the time to enter into this. You can give a very, at the end of it, with the knowledge of afterwards, it's a very simple explanation. You can explain why measurements are given by self-adjoint operators. It takes some work. But then you have the Born rule, that's the thing that I want to concentrate on. The Born rule, and then you have the outcomes. Outcomes of measurements are not predetermined. That's the key issue of this journey. The outcomes of measurements are not predetermined. Also in classical statistical mechanics, outcomes are random, but they are, so to say, predetermined. If you had a perfect knowledge of the state of the system, you could predict every possible measurement in the classical system. Quantum mechanics instead doesn't allow for that. Even if you have a perfect knowledge means to know perfectly the wave function, then outcomes are still random. And then the wave function collapses. I will skip the collapse of the wave function, and this is where the statistical behavior of quantum mechanics emerges. It doesn't emerge from the kinematics. The wave function is the field. It doesn't emerge from the dynamics. The Schrödinger equation is a deterministic equation. It emerges because nature tells you so. And so you embody in a new axiom of the theory. Nature tells us that outcomes are random, and then people at the time postulated that it must be random. Okay, so this is quantum mechanics. Now, we are back 100 years ago, in the 20s. And Einstein, it's famous, Einstein, you probably know that Einstein was not happy. Although he contributed to the development of quantum theory, Einstein was not happy about the development of the theory. Precisely because of this, because of his statistical behavior. And if you read the late papers, like in his autobiography, probably one of the most famous collection of works also about him and also by him, he makes it clear that what he does not like is this pragmatic, let's say, and statistical approach towards nature. So that quantum mechanics is giving up the possibility of a more accurate, at least in principle, it's a matter of principle here, a more accurate description of physical phenomena. Why should we be happy with the statistical description and not aiming at something more fundamental? For Einstein quantum theory was wrong, but not in the sense that it was empirically wrong. Of course, there was no reason to think that the theory was empirically wrong. And actually, even today, there is no reason to think, no experiment contradicts quantum predictions so far. The point is a matter of principle. Is it a fundamental description of nature, or is it only a phenomenological description of nature? And the point of Einstein was that it was a phenomenological description of nature, that another theory should come out where, at least in principle, you can have a more accurate and in principle deterministic, at the end of the day, description of physical systems. Again, it seems like a philosophical debate. We will end up, I just remind you, with the Bell inequalities, entanglement, and then the possibility of using this for doing technologies. So these are important questions per se, and important questions from the practical point of view. So over the years, Einstein, the debate of Einstein somehow evolved over the years. So before, let's say, it was just, let's say, put it on a philosophical level. I think that the correct theory of nature the complete description of nature eventually will be a deterministic one. Once I know the initial conditions, given the dynamics, I end up with the clear predictions, deterministic predictions about the properties of the system and then the possible outcomes of the system. Like in any other theory, classical mechanics, electromagnetism, general relativity are these kind of theories. Once you know the initial state of the system, you know everything about the future evolution and about any other property you want or what you want to observe, whether directly or indirectly. And then he thought that any theory should be. But then, to make the argument stronger, he tried to move, let's say, the debate from the philosophical point of view. You might take this attitude, or you might not take it, to a more physical debate. And it was one of the key points. And again, we are in the 20, and this is it's now called Einstein's box argument, which is the key issue about quantum locality. Quantum locality is behind Bell's theorem, we will come to that, and behind the major problems with quantum. So it's a very simple thing at the end of the day, but very powerful. So Einstein says the following thing. Take a box, put a particle, the wave function of the system will spread, and then after some time, the wave function will be more or less uniform inside the box. It's an ideal, of course, equation. Will be the particle, the wave function of the particle will be uniform inside the box. Very simple. Classically speaking, this would mean that the particle has hit the walls several times, and you lost track of where it is, so it could be anywhere, classically speaking. But quantum-mechanically, there is no particle. There is no point moving like a trajectory, in a trajectory. It's just the wave function that diffuses. It's like putting a drop of ink in water. Now the ink dilutes, and the water becomes uniformly gray. And here is the same thing, basically. The wave function spreads and becomes. Then Einstein says the following. Cut, ideally, the box in two halves without observing the particle. You don't know where the particle is. You just cut in two halves, and you move the two halves arbitrarily away from each other. These are more or less. You separate the two halves. So this is, it's not complicated, but a little bit longer way of saying that you have created a superposition, nothing more. People in the debate, if you read the literature at that time, this has been discussed in many different ways, you just create a superposition going one way or going the other way. Einstein preferred to put it that way. The way this is, again, this is rooted in the superposition principle. So the wave function is uniformly distributed here, uniformly distributed there. You don't know where the particle is. But now the question, that's the key point, is the following one. Einstein argues in the following way. Now there are two ways to consider this situation. One is, let's call it completeness. And incompleteness. So the completeness assumption that refers to the wave function. I don't know if how much you are familiar with these topics. The EPR paper, the key paper of all this line of reasoning. The EPR paper, we will come soon to that, 1935. The title of the paper is, Can the quantum mechanical description of reality be considered complete? So the issue at the time was the completeness of the theory. Complete, what does it mean? Is the wave function, so completeness is with respect to the wave function. Is the wave function complete in the sense that it provides the maximum theoretical possible knowledge about the state of the system, or not? So if the answer is yes, yes, the wave function is everything that nature tells us about the state of the system. There is nothing else. There is just the wave function, that's it, that's nature. So the wave function is complete, nothing to add to it. Or incompleteness. The wave function is important, the wave function is useful, but it's not the whole story. Think of thermodynamical quantities. Once you are given the gas, you are given pressure, volume, and temperature, a classical gas. Pressure, volume, and temperature, you are given everything about the ideal gas from the thermodynamical point of view. But this is not a complete description of the system. A complete description of the system would be the position and velocities of all the molecules in the gas. You might not be interested in that because temperature is enough to know whether it's hot or cold. But from the fundamental point of view, you have also the position of the particles. And then that was important, in the history of physics, was important at some point, thanks to Boltzmann and other people, to prove that thermodynamics is a phenomenological way to deal with classical mechanics. So thermodynamics is not an independent branch of physics. It comes from Newtonian physics. It's an important milestone in the development of physics. So completeness, again, the wave function is everything. Incompleteness, the wave function is something, but not everything. And in particular, with incompleteness, Einstein meant that the particle is somewhere, was somewhere before, was somewhere afterwards, we just don't know where, and the wave function reflects also that ignorance. The wave function perhaps is something more, but also it reflects our ignorance about the state of the system. Okay, now Einstein, so it's again the same thing. Now Einstein argues the following. Let's assume the completeness point of view. So the wave function is everything there is to know. There is nothing else. Now, suppose that Alice, so Alice and Bob will come often in our presentation, just the name of the two observers. So before anyone does any measurement, there is 1/2 probability that the particle is found. So here words are important here when we speak about foundations. Well, so let's say in every branch, but in quantum foundations, common words have a technical meaning. Not only technical words, but also common words. So found is different from being. Being means that exists independently of measurement. Found that only emerges during measurement. So before making a measurement, the particle has probability 1/2 to be on the left, probability 1/2 to be on the right in an ideal situation. Now suppose that Alice performs a measurement and doesn't found, so now Alice measures, and does not found the particle on the left. She looks in the box, there is no light. Then, certainly, the particle is on the right. The particle hasn't escaped. So that's the point. That's the point. The key point of Einstein, that the action of Alice on the left has changed the state on the right. Remember that the wave function, so we are assuming that the wave function this is not our ignorance about the state of the system, there will be the incompleteness assumption. We are accepting that the wave function is the objective state of the system and there is nothing else to do. It's objective state of system. It's like the electromagnetic field, something objective. So the action of Alice on the left changed the things on the right. Mathematically speaking, you know quantum mechanics, what happens that if you measure, you find nothing. So here you have to normalize because of the collapse of the wave function. So here the area is 1/2, now the area is 1. So the wave function has changed here, mathematically speaking. But since the wave function is everything, that change is also a physical change. And so you have a non-local, which mathematically is clear. The collapse of the wave function, once you make a measurement, you collapse of the wave function, and you normalize the wave function. You normalize instantaneously, more or less. As far as we know, the collapse is instantaneous. There is no indication that the collapse travels at the speed of light or less. So when you renormalize the wave function after measurement, so mathematically speaking, that's a non-local behavior. But that's mathematics. The point of view is that if the wave function is the complete description of the system, that also becomes a non-local, a physical non-local effect, because the wave function is the state of the system. And so Einstein says, since it's been fully proved, so we are in the 20s, so special relativity is fully accepted, and by that time also general relativity, even though it was not so much studied, general relativity, but still it was established as a theory, especially because of special relativity, but also because of Einstein's point of view. The world is local, things cannot affect instantaneously other things. Because the world is local, this cannot happen. Completeness implies a non-local behavior. Einstein says, I don't like non-local behaviors, therefore I reject the completeness argument. What happens instead, if I take the incompleteness argument? So I redo the story. So there is the box, the wave function is there, somehow we need a wave function, but the wave function is not the full story. It's part of the story. There is something more, which is the true position of the particle. Well, I should have put it. There is also the true position of the particle. Now I cut the box in two. I separate the particle is here. So the state is like before with respect to the wave function. I don't know where the particle is because I don't have access, so I can control them again. Think the analog here would be the one with thermodynamics. In a gas, you can control by moving the pistons and whatever, you can control the pressure and the temperature of the gas, but you cannot control the position of the particle. The particle keeps moving, so that you cannot control. So here the situation is similar. You control the wave function, would be like the temperature, let's say. You can control, but you cannot control the real position. So you don't know where the particle is still. Then Alice makes a measurement, doesn't find the particle here, then the particle must be there. But you see that in this case, at least that's what Einstein thought. Then Einstein was wrong here at the end of the day. We can't do it. But now, let's follow the steps. So then, at least the hope of Einstein, let's say, was that, sure, the fate of the wave function is the same one as before, the fate of the wave function. Alice measured, she didn't find the particle, the wave function collapses, then the wave function is fully concentrated in this half of the box. So it's, again, mathematically speaking, it is a non-local effect. The collapse is non-local. So the wave function changes non-locally here and there. But the point is that now the wave function is not directly related to reality. Reality is given by the position of the particle in the box. And the particle was all the time on the right. It's not that Alice destroyed the particle, was like ink that was diluted up here, up there, and then it pops all of it on the right. No. The particle is more or less, I mean, for all practical purposes at least, it's a point particle. It was always on the right after we put the divide. And it's Alice, the opening of Alice, of the box, just revealed a property that was pre-existing. The particle was already on the right. The action of Alice in opening the box was nothing special. It's like classical physics. When you do a classical experiment, you put the particle in, I mean, someone for you puts the particle in one of the two boxes, and then you have to look. It's not here, it means it's there. There's no mystery. The particle was there even before. Clear? I hope. Because once you've been trained with quantum mechanics for many years now, it's difficult to go back to classical reasoning. So it's very naive. Einstein is taking a very naive, simple-minded attitude towards the problem. Not sophisticated. But I hope you can appreciate the change of Einstein. So Einstein was not just complaining about the statistical character of quantum mechanics because of his philosophical view towards it. He now was given a physical argument. Completeness, which means standard quantum mechanics, which is the things that people teach, I also teach at the university. The completeness idea that the wave function is everything there is to know about the state of the system, brings to non-locality. The world is local, therefore incompleteness is not correct, completeness is not correct, then the theory is complete. Okay, so that's it. Incidentally, I just anticipate something that probably you've already heard. The world is non-local. It's quantum non-locality. That's the bottom line of the stuff. We will come to that. But now we are in the 20s. 100 years ago, people didn't even have the faintest idea of what was about to come. So that's it. The next step, and this argument of Einstein was given. Oops. Now I'm in trouble. But it takes some time, so. Some water, I don't know, alcohol. Okay, good enough for now. So we come to. So the box argument was presented in a letter, if I remember correctly. So it was part of a standard correspondence among scientists, and it didn't really go that far. It was basically neglected, and only in more recent years it was discovered by the historians of quantum mechanics. The paper that really started to change things is the one in 1935, the EPR paper. So that's probably you have heard of. That's from the name of the three authors, Einstein, Podolsky, Rosen. If you Google it, you find it immediately. Again, so the story, as I will present it now, the story is exactly, there is nothing, so from the conceptual point of view, there is nothing more than what I told you before with the boxes, the argument of the boxes. It's exactly the same story, and actually it seems that Einstein himself, it seems, was not so much happy about this paper. It was, because it seems, I mean, the comment is not fully clear, because it adds, according to Einstein, it adds extra structure to an otherwise simple argument. So it doesn't go directly to the point. But again, Einstein was wrong here, because it was important, actually, to go through this argument here for what happened in the following. Of course, I mean, after 100 years, it's easy to say Einstein was right, Einstein was wrong. Einstein was an extremely intelligent person, there is no question about it, but he also failed from time to time. Okay, so the EPR paper, again, the title is Can the Quantum Mechanical Description of Reality Be Considered Complete? Correctly, so the issue is completeness of quantum mechanics. So it's simple, and the story is the same as before. But now the crucial ingredient comes that no one, basically, at that time, appreciated in its consequence. The crucial thing is that now there is not just one particle, the particle in the box, but there are two particles, and the particles are entangled. So this entanglement now is a common word. Now there is also a book, Entanglement Explained to Babies. So if you wish, small kids, you find a book to teach entanglement to very small kids. And you have the single state. So I hope you are familiar with Are you familiar with single state? I don't know. All of you, your background seems yes. If no one is not, just raise a hand and a 30 seconds explanation of what it is. So you have two particles in this entangled state. This entangled state is rotationally invariant. That means, so that it's 2 1/2, no? It's a 2 1/2 spin particle, so the spin can be up or down along any given direction. These are entangled in the sense that if the particle on the left has the spin up along one direction, the other particle has the spin down along the same direction, and vice versa. Since this state is rotationally invariant, that's why it's called a single state, that refers to any direction. In any direction you measure, the spin has probability 1/2 to be up, and 1/2 probability to be down in any direction, and then the opposite will happen to the other side. The key feature of this state is that the properties of the two particles are correlated. In this case, actually, they are anti-correlated. That's not important. So often, how we speak of correlation, it's anti-correlation, opposite properties. It's a type of correlation. And that basically, again, it's the same story like the two boxes, the two half boxes. Also, their properties were anti-correlated. If the particle is in one side, it will not be on the other side. It's the same story. And now you know what happens, so if you heard of it, the two particles, so this state entanglement refers to the internal degrees of freedom, the spin of the two particles, but then the two particles, electrons, probably whatever, ions, have also a spatial component of the wave function. There is usually you write down only the spin part. There is also the space part of the wave function. The space part of the wave function, you draw it. The wave function is such that one particle moves to the left and the other particle moves to the right. And here again, there are Alice. There are Alice and Bob that make measurements. And then, exactly with the box spin, before the measurement, there is 1/2 probability that each of them will find a particle with a spin up or a spin down, like in the case of the box, 1/2 probability to find or not to find the particle in the box. If Alice measures and finds the spin up, for example, along a given direction, we know that Bob, 100% probability, before it was 50-50, so let's say, let's write it. So before the measurement by Alice, Bob has 50% probability to find the particle up and 50% probability to find the particle down, but after Alice made the measurement and found the spin up, there is 100% probability that Bob finds the particle down, the spin down. So again, things change. Again, sorry if I insist on it, but because that's the key point throughout the discussion. Probabilities have changed. Now again, that's again in classical mechanics, in classical statistical mechanics, not even statistical, classical mechanics, they will be the same, because take similar situation takes again that now we have two particles. So now the game of the box will be, I have two boxes. In one I put a blue particle, and in one I put a red particle, a red ball, classical macroscopic ball, blue and red, and I separate. So before opening the box, classically, there is 50% probability that the particle, I keep one box and I give you the other box. So before I open the box, there is 50% probability that you find that you have the blue particle, and 50% probability that you have the red particle or ball or whatever. But when I open and I find that I have the blue one, then there is 100% probability that you have the red one. No? Very naive situation. But this naive situation means incompleteness. Means that the color of the particles were there before, existed before the measurement. It's just that we didn't know what color it was. By opening, I just learned about the color, and then probabilities change. These are what are called epistemic probabilities. They depend on it's our internal knowledge. It's not, nothing happens to the particles. The particles were blue and red before and will be blue and red afterwards. So it's my non-local knowledge, who cares, but the physics is local. That's the point of view of Einstein. But if we take, so here it will be the same. If we take that the spin properties were already defined before the measurement, the outcome would have been up. So nature knew that the outcome was up before Alice performed the measurement, because that was it. That's how it was. So the measurement by Alice simply reveals the pre-existing property. The spin was along the direction. And so nothing happens on the left. But if we take, on the right, but if we take the completeness assumption, so that the wave function, so that this single state is the full description of the quantum system, so there is everything there is to know, there is everything that nature gives to the particles, that's the true objective state of the system, then the measurement by Alice with the subsequent collapse of the wave function changes the physical state of the system, and it has a non-local effect. So I hope, so ask me if I'm not clear, because that's the whole story. So again, it's like the boxes. If you see, it's more complicated. That's why Einstein was a little bit unhappy. It's the same story. So completeness, I write it again. Completeness implies non-locality. Because the completeness assumption means that the wave function is the objective state of the system. You should think of the wave function like the electromagnetic field. Just to speak about fields or whatever, water field, whatever field you want, gravitational field, let's say the electromagnetic field. It's like the electromagnetic, if by measuring a charge, so in electrodynamics this is not possible, but suppose that by measuring the value of the charge here, you change the electromagnetic field instantly, you have a non-local effect. The Coulomb force, if taken seriously, would be like that. The Coulomb force, now if you move a particle here, you instantly change the field everywhere, and you move all other particles instantly. It's a non-local. Here, the story is different. If the wave function is an objective description of the field system, which would be implied by completeness. Completeness means that there is nothing else. So either science is completely a dream, a subjective, I have my science, you have your wave, it's not acceptable. But if the wave function is objective, observer independent description of the system, then it's non-local change, is a physical non-local change, so the theory is non-local. And so again, Einstein rejects non-locality, Einstein, and then rejects the completeness assumption. The wave function is fine, it will be an ingredient of the theory, but it's not the whole story. It has a subjective ingredient. The spin properties existed before, we were just ignorant about these properties, and the wave function summarizes. And in fact, the conclusion of the EPR paper, I go by memory, more or less, is why we proved that quantum mechanics is incomplete. So the title was the quantum mechanical description of reality be considered complete? The argument is meant to answer no, it cannot be considered complete. So while we proved that the quantum theory is incomplete, it remains open how to find the new theory that completes the quantum mechanics. That was part of the last years of life of Einstein to work in that direction. It never succeeded because it's a difficult job, as it's proven, but mainly because the world is not local, because Einstein was wrong. But that's okay, we will come to that. So, I summarize the logic of the EPR paper because it's important for all that. So basically, the argument is the following. So one ingredient is locality. So these are the ingredients. So locality. So the requirement of locality of physical laws. And what now are called, at the time were not called like that, EPR correlations related to entanglement, but actually you don't need the box argument tells that you don't need entanglement. You just need this correlation, the fact that the wave function is a superposition, and if something happens here, then the opposite happens there. So locality plus the quantum correlation, if you wish, yeah, correlation, implies incompleteness, or what is called in more modern language, local hidden variables. LHV, it looks like a disease, it looks like, in the field, it's a shorthand for local hidden variables. So hidden variables in the sense that it would be, again, the idea that people has in mind are like the position of the particles in the gas. You don't see the particle, the position of the particle. You just feel the gas as a whole. But there are positions, so in that sense they are hidden. You cannot have an easy experience, let's say. Perhaps one day, who knows? But at the moment you just feel some macroscopic effect which is governed by the wave function. So local, and they are local, of course, local. So this is basically the EPR. The EPR argument. Note that in the popular literature, especially, they talk about the EPR paradox. There is no paradox with EPR. So it's not a proper way of describing it. There is no paradox. I mean, you can always frame it as a paradox if you wish, but it's an argument. You give an argument to support incompleteness using locality. Okay, let me see. So now I will stop. Okay, so 1935, the thing died there. Oh, by the way, eventually Heisenberg, in commenting these arguments by Einstein, he acknowledged that the completeness position, so he was an orthodox, he heavily contributed, Heisenberg, not to the development of quantum theory, in his orthodox formulation. He was convinced that quantum physics represents a radical change with respect to the classical way of doing physics, and in particular the wave function is a complete description, that we have to give up any further intuition about the nature and behavior of physical systems, and he acknowledged that there is a form of non-locality. He clearly acknowledged that. He tells, and then we will come to that you cannot use it to do faster than light. You know, there is no signaling theorem in quantum physics, and we will see the reasons for that. But he acknowledged that there is a non-locality. But apart from this, the Einstein's complaints were mostly ignored for a very simple reason at the end of the day, is that the first reason was that probably there was a war, World War II, that people were busy with other things, in a way or another. And also because quantum theory was a very successful theory. So when something is successful, you can abandon it. And in fact, we have to wait after the war. At the end of the day, we have to wait 1964, when Bell comes. So this is basically will be part of the next hour. So I will just introduce that and we will go to Bell. So you see, 30 years, well, it's not much if you think about our lives, 30 years is a lot. But if you think of the development of physics, it's not. And so, so as I said, Einstein was right in one thing about the complaint about the EPR paper. It seems that it was mainly written by Podolsky, even if it brings the name of Einstein. So was right in one thing, that from considering the knowledge at the time, the EPR paper didn't bring anything new with respect to previous arguments and simpler arguments with just one part. And that is true. Non-locality, you don't need two particles to argue about non-locality. One particle is sufficient. But, and they couldn't know that, of course, it would have been to ask too much from Einstein. He couldn't know that actually they were using the key ingredient for the future development, which is entanglement. But is the, now we know this now, but at the time it was not clear. That actually, when you have two particles, the two particles are different, are correlated in the entanglement state. The non-locality becomes experimentally detectable. That is the big difference between one particle and two particles. And in the 60s, John Bell was thinking about these issues. John Bell was unhappy with the state of quantum mechanics, as Einstein, also Schrödinger were. He wanted to have a better description of physics. A better description of physics seemed to be available. It is Bohmian mechanics. If we have time, I will tell you about that. So I was originally supposed to start with Bohmian mechanics, but then I thought and collapse models, I will do it at the end. I will go this way. So if you have time, we will talk about it. So there was a description that was a complete description of physical systems, Bohmian mechanics. But Bohmian mechanics is what I showed you before, what was there. There are, particles are there. There is the wave function, but particles have positions. So, and that also, so that, for example, explains one thing, that when you hear in the news, but also in scientific paper, by experiment, we proved that particles don't exist. That is a horrible thing to say, because a physicist cannot prove that things don't exist. The particles, something. That particles don't exist, don't have a position, they cannot have a position, that's fully wrong. There is Bohmian mechanics, it's a consistent theory, and particles in that theory, and in that theory particles do have position. So it's not against experimental evidence to have a position all the time, not sometimes, to have a position all the time. So he knew about Bohmian mechanics, but Bohmian mechanics is an openly non-local theory. It's clearly non-local in a gross sense. It's even worse, and we will come to that, it's an important thing. It's even worse than the Coulomb potential. The Coulomb potential is non-local, no? Because it's a force, instantaneous force, but then it's been, you can correct the Coulomb potential with electrodynamics or for electricity or general relativity for gravity. You can correct that. The non-locality of Bohmian mechanics, which is a non-locality of entanglement, is a completely different nature. And that's one thing. I will not tell that now. And then he tried to make it local. Okay, it's a non-relativistic theory, no big deal. Let's try to make it relativistic. So what's the problem? And then he didn't succeed, and he stumbled into this one. And then we will see what he did not do. And now what he did, probably you know, it's very important at the end of the day. But how he arrived there, that's perhaps less known, and it is something interesting. So I think I can stop here, for now, and I leave the stage to him.